Welcome to the course on scalable data science. I'm Anirban from IIT Gandhinagar, and today we'll be talking about multi-probe LSH. So, we talked about the problem of finding near neighbors, and just to recap this problem, we are given a set of data points, let's say x1 to xn, that lie in some d-dimensional space. We can pre-process this data set as we want, and then at the query time we are given a particular query point q. So our question is that we have to answer what is the nearest data point to this query, right? And then there are various versions of this question. We could be asked the question of finding out the k nearest neighbor to this given query, or we could be asked the question that given the query point and the radius r, return me any point that lies within the distance r of the query point q. Okay. So we also looked at the problem of the algorithm of locality sensitive hashing as a potential solution to this problem, right? And again, just to recap this, what we are given is we are given the version of the nearest neighbor problem where the input radius is also specified, right? So now we are solving an approximate version of this. So we are given a radius r, the input data, as well as an approximation factor c and a confidence delta. Okay. So what we have to return is the following, that if there is any point in your input data that lies within distance r of the query point, right, then with probability 1 minus delta you have to return one that is a distance at most cr. So c here could be is bigger than 1, right? So we are returning an approximate near neighbor, right? We don't need to return anything that's less than equal to r, but we certainly need to return any point that's less than equal to cr. So how did we do this? What we mentioned, and let's think about when the distance metric is the Euclidean metric for now. Okay, what we said is that there are two main parameters of the locality sensitive hashing. First is k, and the other is l. Okay, so what do we have to do? So we'll build l different hash tables, right? As in this picture, we'll build l different hash tables, and in order to create one hash table, one of these hash tables, we choose k hash functions, right? Let's say we are building the ith hash table. Now for that we need to choose hi1 to hik, right? And each of them are IID, and they are being chosen from some hash family. The hash family depends on the particular distance metric that you're interested in. We talked about a number of different kinds of metrics and their corresponding hash families. If you don't remember all of them, just think about the Euclidean metric and the corresponding hash family. Now for the Euclidean metric, this is what we were doing. So if we had the input points, we were first drawing a random line in space, right? Then we were projecting that line, then we were projecting the input point onto that line, right? So this is the projection of the point of this point onto this line. And then we bucketized, right? So we created these intervals of size w, right? And then we return the ID of the interval that this projection lies in. Okay, this is one of our hash functions hi1. So this gives me an interval number. Okay, and you have to do this k times, and then you have to concatenate them. That gives the index for the ith hash table, right? So the ith hash table is created by putting the point x in the bucket that is specified by this k tuple. Okay, so of course there are potentially many number of buckets. Not all the buckets will have points in them. So after we have created the hash ID for all the points, what we will do is that we will store these non-empty buckets in a normal hash table. That is, we will use just a standard hash table to actually store to actually instantiate the table hi. Okay. Now what happens at query time? At query time again we'll do the same. given the query Q, we will find out which bucket Q lies in the first hash table, which bucket Q lies in the second hash table, and similarly for 1 to L, right? And then we'll take the union of these candidates, right? In the sense that we'll take all the points that have fallen in the bucket H1Q, all the points that have fallen in the bucket H2Q, and all the points that have fallen in the bucket HLQ. We'll take the union of them. So remember, these buckets are not necessarily disjoint because each HI contains all the data points, right? All the data points have been mapped L different times. Yeah? So HI, and then you take the union of HI1Q, HI2Q, HI3Q up to HLQ, right? So these are your candidate near neighbors. Now, not all of them will be at distance less than or equal to CR. So what you will do is that you will go over this list of candidates. You will then compare each of these candidates to Q itself and throw away the ones which are farther apart, whose distance from Q is more than CR, right? So then there are two issues, right? So the complexity, the query time complexity depends on the number of candidates. Okay, and the space of the algorithm is proportional to L, which is the number of hash tables. Okay, and our aim is to try to minimize these two. Okay, so as we saw that there are a number of interesting space-time trade-offs that locality-sensitive hashing does, and more importantly, what it does allow us is to do the following: that it gives the first provably sublinear query time algorithm for approximate nearest neighbors. Okay, so if you remember that what we could do is to set that L equal to n to the rho, and we could also have a query time which is order n to the rho, right? And rho is typically a function that depends on C. Okay, it could look like something like 1 to the power 1 plus 1 by C. Okay, sorry, yeah, n to the power 1 plus rho, and rho depends on 1 by C, order 1 by C. Okay, so the space is n to the power 1 plus rho, and the query time is n to the rho, and rho is of the order of 1 by C. So while theoretically this is a breakthrough, in practice it has its problems. So what are we doing here? We're trading off space with time, right? Remember that the naive solution was to do a linear search, and in linear search space required would be n. So we're trading off space with time, and we have a strongly superlinear space. Okay, and even in practice this shows the space required by a standard, a typical locality sensitive hashing data structure is of the order of 5 to 20 times more than the memory taken for the data set itself. And this is sometimes a problem, right? Because our data sets are typically very large. And frankly, while theoretically it's an excellent algorithm and has found a lot of practice, most of the practical applications have lied in the regime of when the dimension is medium to high, when the dimension is of the order, let's say from 100 to thousands, of that order. Okay? And the vectors are fairly dense. Right? In that setting, the space required, the space-time trade-off that is achieved by the locality-sensitive hashing algorithm compares very favorably to the space required and the time required for standard linear space, right? For standard linear search, right? For the naive linear search. Beyond this, if the dimension becomes very, very big, or the data set becomes very, very sparse, naive search typically just beats locality-sensitive hashing algorithms. There is an interesting sort of interesting set of research here, in the sense that if you look at the lot of recent advances in machine learning, they're really trying to get dense embeddings for sparse vectors, right? And in that sense, locality-sensitive hashing still continues to be a very sort of appropriate technology for different machine learning algorithms. So, can we do better, right? And since space is our main concern, what we want to see is that can we reduce space? we have to do some trade-offs. So can we reduce space while not affecting query time by too much, that I'm willing to pay a little more when we are doing the query, right? Not as bad as linear search, but maybe a little more than what I'm sort of promising in the locality sensitive hashing algorithm, but I want to reduce the space drastically, right? So the idea, the basic intuition behind such data structures is to probe multiple times, right? So imagine this thought experiment, that suppose for a query, right, we knew that which are the buckets that have the highest probability of containing the near neighbor of that query. Okay? So a natural algorithm that knows these probabilities would then go and probe these buckets. Right? So the standard locality sensitive hashing algorithm is probing only one bucket per hash table. This ideal algorithm, if it knew that some other buckets have a non-trivial probability of containing the near neighbor, it would also probe that other bucket. So it would probe multiple buckets per hash table. Can we implement this algorithm? Okay. So the basic problem is as follows, right? So how do we know this particular probability distribution? Okay. So computing this probability distribution is as hard as really doing a linear search again. So can we approximate this probability distribution in a smart way? And this is the basic elegant idea behind entropy-based LSH. This was developed by Reena Panigrahi in 2006. So what it says is as follows, that assume we know the distance RPQ. So here is the query point, and this is the nearest neighbor P, and this distance is RPQ, and assume that we know this distance. Okay. So the intuition is that the buckets are a random partitioning of the data, right? And this random partitioning happens as follows. That suppose here is the data, right? Now based on the hash functions that were chosen, the data gets partitioned like this. Okay. So, and because of the properties of the locality sensitive hashing algorithm, the success probability of a bucket, right? That is the probability that this bucket contains the point P, right? Depends really on the distance RPQ. Okay. So ideally, if I can sort the buckets with this probability, right? If for every bucket I could calculate the probability, if I knew RPQ, right? If I could write down the probability that this bucket contains the near neighbor P, right? And then if I could sort the buckets with this probability, then I would look at only the top few buckets, because I don't really want to look at all the buckets because that's too expensive. So then I would only probe the top few buckets and be done with it, right? But calculating this probability exactly is again hard for all the buckets, right? It's very expensive. So what Panigrahi does is that he gives a very elegant way to sample from this probability distribution without actually calculating this probability for every bucket, right? And the way to sample is as follows. What he notes is that suppose we take the query point and we build the radius RPQ. We build the ball of radius RPQ around the query point. Okay? So, and then we sample multiple points at this radius. Okay? And then we hash these points using the same set of hash functions, right? So what he notes is that buckets that, because the probability that a bucket contains the near neighbor P is dependent depends only on the distance RPQ, right? Then all points on the surface of this sphere have the same probability of falling in the bucket, or in that particular bucket, right? And in that case, if I take multiple points from the surface of this sphere of radius RPQ, right, and look at the buckets that these points fall in, right, then the buckets that are more likely to contain P will come up more often. Right? So what it means is that the algorithm is as simple as follows. Right? That take the query point Q, right, make a guess on the distance RPQ, sample from the multiple times from the ball, from the surface of this ball, which is the ball of radius RPQ around the query point Q, and then look at the buckets that these points fall in, right? And now consider, and this is all happening in a single hash table, and then we take all the candidates that these buckets have, all the query points, or all the data points that these buckets have, and these are our candidates. So technically, even if you have had only one hash table, right, you get to probe multiple buckets and consider their candidates, right? And Rina has a very nice theoretical guarantee on this entropy-based LSH. We won't go into the details of the theoretical guarantee, however. What we will look into is a modification of this scheme. Okay, so the modification of this scheme is something called multi-probe LSH, and this is really the same idea in a slightly more efficient manner. What it says is as follows: that look, sampling first from the surface of the ball, and then looking at the hash buckets is pretty expensive. What we will do instead is that we will look at the bucket that this query point has fallen into, and then we will perturb the idea of this bucket a little bit, right? So what does this mean? Let us look at this in the very specific case when we have a LSH, when we are building a LSH table for L2, right? Remember what we were doing there? We were taking a random line, right? This is the line V, right? This is the query point. First we project Q onto V, right? So this is Q dot V, and then we bucketize them in buckets of size W and apply a random shift. So this is a shift, right, that is drawn uniformly from 0 to W. Okay, so the hash value of Q is this ID, the ID of this bucket. Okay, so then imagine that there is some other point P that is actually pretty near to Q. Okay, so then if P has not been assigned the same ID as that of Q, right, then it is likely that it falls maybe either here or here. That is, if it's not in the same bucket as Q, then it's likely that it's in a neighboring bucket, right? Which means that the two buckets, that if I don't find, if P does not happen to be in this bucket HVBQ, right, then it's probably been assigned HVBQ plus 1 or HVBQ minus 1. And these are two immediate sort of possibilities, the most likely possibilities of the hash value of P under this hash function, right? So this is what we'll try to phrase, that instead of actually doing the perturbation on Q and then figuring out what the hash buckets should be, we'll do the perturbation directly on the hash indices itself. Okay, so just to be very specific, right? Supposing k equal to 3. Okay, so the first hash table has the buckets that are tuples of 3, has bucket IDs that are tuples of 3. Okay, supposing H1 is the first hash table, so, and suppose Q falls in H1 of Q, which is 583. So then the immediate next ones would be to look at 5 plus 1, 8, 3, 5 minus 1, 8, 3, 5, 8 plus 1, 3, 5, 8 minus 1, 3. You get the idea. Okay, and these are buckets that differ in only one of the positions from the query bucket. Once we've exhausted them and looked through them, then we could also start to look at buckets that differ in 2 positions, right? Maybe 5 plus 1, 8 plus 1, 3, 5 plus 1, 8 minus 1, 3, and so on and so forth. Okay, and then buckets that differ in 3 positions, and so on. And this would eventually give me all the buckets, right, that differ in at most, let's say, S positions. Okay, so how do we do this in a sort of principled way? Okay, how many buckets do we get to choose? Should we really be searching for? And is there a particular order in which we should be doing these perturbations and so on? So in order to analyze this, let us formalize this a little bit, right? So let me consider this delta call delta to be a perturbation vector. So it's something very simple, right? So suppose in the case when k equal to 3, right, the deltas look like, let's say -1 0 1 plus 1 -1 -1 0 plus 1 -1 0 and so on, right? Which means that it's basically all possibilities having where each bucket is being perturbed either by a plus or a minus, okay? And there are and some bucket might not be perturbed, right? In that case, some bucket ID might not, some specific ID might not be perturbed, in which case you have a 0 in delta. So given a bucket HQ, we get a new hash bucket by doing HQ plus delta, right? And suppose delta has at most S non-zeros. So this S will be a hyperparameter that's kind of chosen based on the amount of time you want to spend in query and so on, right? So for instance, think of S equal to 1, right? That is, I only want to look at buckets that differ from the original bucket in only one position, right? Then what is the and for a general S, then what is the possible number of this delta, right? So the possible number of this delta is that you have to choose S positions from k positions. That happens in k choose S, right? And each of these positions gets a +1 or -1. So that's 2 to the S, right? So once you fix S, the number of possible perturbations you can get is k choose S times 2 to the S. And this is for a single hash table, right? We could be, if there are multiple hash tables, then we should really be doing this independently for each of the hash tables. Okay, so this is fairly large, right? Once S gets to be a little big, this increases quite fast. So is there a natural way to order these buckets for searching, right? I mean, you could potentially sort of already have an idea about this. If you say that once you start thinking about that if a neighboring point is really close to Q, then it's more likely that it will fall in a bucket of 0 or 1 perturbations than 2 perturbations. So we should really search the buckets with 0 that has at most 1 perturbation before we search the buckets that have at most 2 perturbations maybe. And we should search 1 perturbation and 2 perturbation buckets before we go to searching 3 perturbation buckets, right? But is there a better way to structure this search? So here's a very interesting way, right, that was proposed by the original paper of multiprobe LSH. And what this says is that let us look at the actual projections of the points, right? That is, suppose this was the line V that we were drawing before, right? And this is the projection of the point Q. This is the projection of the query point Q, right? So Fi of Q. So this is the ith bit, let's say ith hash index ID, and this is obtained by Q dot Vi plus Bi. So Bi is the random shift. Okay, so now Vi is chosen according to uniform distribution on the sphere. If you remember, equivalent way of looking at it, Vi is chosen according to N0 ID, which means that every index of Vi is a vector of d dimensions, the same dimension as that of Q, and every index is a Gaussian distribution from n0 1 over square root d. Okay, now if I know this, then I also know the distribution. If some point P, if the projection of P is Fip, right, then I can actually write down what is the distribution of Fip minus Fiq. Okay, so so remember that Fip minus Fiq is really a random variable because of the random choice of Vi, right, and Bi, right? Vi and Bi are the random variables here. So therefore, the distance Fip minus Fiq, right, is really Q transpose Vi Q minus P transpose Vi. Right? This is this random variable Fiq minus Fip, and it's if you know about the properties of normal distribution, you can easily say that this particular random variable, right? This particular random variable has a distribution of this form. That is, it has mean 0, right? And the variance is dependent on the L2 norm of P minus Q. That is on the distance RPQ. Okay, the variance depends on that, right? So what that means is as follows, that let me draw in this in here, that here is FIQ, right, and I'm drawing the distribution of the random variable FIQ minus FIP, and so it's a Gaussian that is centered at FIQ, right, and the variance depends on this on the norm P minus Q. Okay, so notice, and let me define two more quantities. Let's say that these are the boundaries. Remember, we bucketize these projections, right, into buckets of length W, right? So let's say that these are the boundaries of this bucket. So this is the bucket HIQ by definition. This is the bucket HIQ minus 1, and this is the bucket HIQ plus 1, right? And so these are the boundaries. So let's say the distance of FIQ to this left boundary is denoted by xi minus 1, and the distance of FIQ to the right hand side boundary is denoted by xi1, right? So what you can now intuitively see is that the probability that this particular FIP lies to the right hand side, lies in the bucket HIQ plus 1, will depend on this distance xi plus 1, and the probability that FIP, right, lies to the left hand side, lies in the bucket HIQ minus 1, will depend on xi minus 1, right? So let us do this formally, right? And by doing so, we'll be able to assign some kind of likelihood. We'll be able to estimate the success probabilities of each of the buckets HIQ minus 1 and HIQ plus 1. Okay, so if I were to write down this probability, right, you could say that the probability that HIP is, because this is a normal distribution, the probability that HIP is equal to HIQ plus 1 will then depend on exactly the PDF of the normal distribution, which is EXP of minus some C times xi plus 1 square. Okay, because this distance, and the C will depend on the radius also. Okay, so that means, what that means is that the C will depend on the distance P minus Q, right? So what that means is that now we can assign success probabilities to the perturbations plus 1 and minus 1 for this particular index HIQ. Okay, let us write down this in a slightly more formal again, that supposing the perturbation vector capital delta is delta 1 to delta k. Remember that each of the delta i's is either minus 1, 0 or plus 1. Okay, then what I could write down is that the probability that HIP equals HIQ plus delta, right, is nothing but the product of the probabilities, because for each I the hash function hi is independent of each other. So it's the product of the probabilities that HIQ equals HIP, this should be P, HIP equals HIQ plus delta I, and again delta I is either minus 1 or plus 1. And by the previous calculation that we did, that this depends on really the distance of FIQ from the corresponding boundary, right, which is given as xi delta I, right? So it's the product. This can be I've kind of hand waved this a little bit, but this can be written as the product of the exponentials of minus c xi delta I square, which the product translates to the exponent, and we get a exp of minus c summation xi delta I square, right? For instance, if delta is plus 1, 0, minus 1, you would get x1 plus 1 square plus x2 0 square plus x3 minus 1 square. Okay, this would be the exponent. So now this allows us to define a score, right, a score for each perturbation vector delta, right, and that score just depends on this on the quantity in the exponent, right? Because we want to maximize the success probability, we want to minimize the summation xi delta I square, right? Because if this is minimized, right, then the success probability will be maximized. The lower the score, the higher the probability of P being in this bucket. So then what we do is to order buckets by this score and search them in this order. So when a particular query Q arrives, right, we then create the order in which the buckets, and we then want to sort the buckets according to the score delta, right? And remember that the score delta depends on the query queue. So how do we do this efficiently? First, we calculate the xi plus 1 and xi minus 1 square for I equal to 1 to k, and then we sort them. So let's say that the sorted values are z1 to z2k. So there are 2k values because each index gets either a plus 1 or a minus 1. And beyond that, it's really a sort of mean heap based algorithm, right? Basically what we will do is that let's say that I equal to 1, right, has the minimum xi delta I, right? The z1 contains the minimum xi delta I, okay, of these values. So then we start with that, right? And then we either at every step we either keep on expanding that, right? Either add the very next one, right? I mean, for instance, if 2 is the next highest, if 2 is the next smallest value, either we go from the set 1, which is the bucket ID 1, to the bucket ID 1 2. So bucket ID 2 would be the next one to explore, or we go from bucket ID 1 and we replace that by bucket ID 2, right? So at every step, right? So we could define a search procedure in which at every step we either go to replacing the max of the max value with the next max value, or we augment it with the next max value, right? So this gives us a way to search through all the possible buckets, right? So we first search bucket 1, and then we either first search bucket 1 or bucket 1 2 together, and so on and so forth. Okay. So in practice, we kind of have a query time budget, and we stop after that. Okay. So in terms of experiments, what this shows is that this is something that is really effective in reducing the space. For instance, I'll just point you to one of the plots. In one of the plot, in the y-axis is the recall, which means the fraction of near neighbors that we have been able to, let's say the fraction of the nearest neighbors that we have been able to return using LSH. And on the y-axis is the number of hash tables. So if you see that the multiprobe plot, right, uses much less hash tables than, let's say, the basic LSH plot, right, and for the and it is able to, let's say, this point, right? So using the same number of hash tables, this gives a much higher recall. Or rather, if you want to look at it this way, that if I want to achieve 0.9 recall, number of hash tables we need here is let's say only 6 or 7. Number of hash tables we need here is of the order of 32, 33 in the basic LSH. Okay. So just to summarize, the LSH is a powerful technique, but there are few areas of concern. Memory usage among them. The entropy and the multiprobe LSH are elegant solutions that are very useful in practice, and they also form part of the state-of-the-art locality sensitive hashing system. And the basic intuition that you should remember is that we want to probe multiple buckets in a query dependent manner. Primary reference for this lecture was this paper on multiprobe LSH by Chin Liu, Josephson, Wang, Charikar, and Lee, which appeared in VLDB, and also the paper by Reena Panigrahi on the entropy-based LSH. And thank you.